Hey everyone, welcome to another one of our conversations with an astrophysicist. My name is Scott Lewis, your host, and with me, as always, and I think we're just going to keep doing these forever until the end of time, or at least the heat death of the universe, is Dr. Katie Mack from the University of Melbourne, Australia. How you doing, Katie?
Good, good. How are you doing?
I'm tired, but that's okay because it is now officially Saturday and we can get going with some science. Like I was talking to you beforehand, we're going to do a little bit of housekeeping real quick. So, as some of you might notice, we are on a different channel right now. We are on Know the Cosmos, which is a project I started a few years back. But you might be seeing us over at Space Fan News, which is where we started these. So we had a series on dark matter, on supernovae, so I've included links and doobly-doos all over the place to the playlist for that. But we will be moving everything over to Know the Cosmos, and also some new future projects that are super secret right now with Katie and also Alan Duffy, or Astro Duff, as I'm learning that he prefers to be called. But we will be releasing that out as soon as that's completely done. But we do have a Twitter account, so we are at Know the Cosmos. I have a website set up that's still under construction, but it's still going, so knowthecosmos.com. We're on Google+, we are on Facebook, everywhere else, so like, subscribe, follow, all that fun stuff, because we're going to be continuing this. Also more awesome videos on mainly astronomy and cosmology, but also digging into many of the other sciences and finding a good bridge between humanity and our experience of the universe and how we better know the cosmos from that. So that's housekeeping. You can contact us as we're going through on YouTube, so you can leave us comments over on YouTube. I'm already seeing one from Craig Landon, so hi Craig. Thank you for joining us over here. You can also use the Q&A app, which you can see either on YouTube or on Google+. So that is available there. So on the very bottom left, I believe it is, you'll be able to pop open. You can ask those questions. So we'll see them popping in, and if we enter it on air, it'll create a timestamp, and you can actually go through all the different questions that we answer while we're live. So well, actually, no, let's just get started. So we are talking about what I have been corrected on earlier through academic peer pressure. It is no longer the cosmic microwave background radiation. It's just CMB, the cosmic microwave background. So thank you to Katie and to Summer for correcting me on that earlier today. And how, yeah, like I think it's a good testament to how this is something that we've known about for a few decades, but we're knowing more and more about it, and so there's even some paradigm shifts in how we're describing it and what it actually is. So let's start with an introduction. What is the cosmic microwave background, and why is it no longer CMBR?
Okay.
Is there a reason, or just to be more efficient with hashtags?
So I think it just, when it was first discovered, they called it CMBR, and then we got used to it, and it's just cosmic microwave background. So yeah, I don't know when the change happened, but there's a difference, I think, between when people call it CMBR or CMB. But most people these days call it CMB. Okay, so the cosmic microwave
all the cool astrophysicists are calling it CMB.
Yeah.
Okay. I like that crowd, so I'm going to try to fit in a little bit more.
Okay, good. Okay, so the CMB was discovered in around the 1960s, and what happened was there were these two physicists working at Bell Lab, and their names were Arno Penzias and Robert Wilson, and they had this microwave detector. And do you have a picture of them standing next to their microwave detector? It's a weird looking.
I can get it up, but you didn't share that folder with me that you were collecting.
I did. Oh no. Okay. I will
but
do that.
That's fine. I actually had one up. Let me get this up here. So and the reason why I love this story so much is because I am a juvenile at times, and when they were getting their readings, they no, this is weird. Why are we getting this this. It just looks like noise, and they thought there was pigeon poop all over the horn.
Yeah. So okay. So I just shared that folder with you, but if you find the picture, right. So okay. So these guys had this micro detector, and they were trying to do something sensible. I don't remember exactly what it was. And they had there was this hum in their detector. There was this like static, and everywhere they looked in the sky, they had this static, and they couldn't get rid of it. And they thought maybe, like Scott said, maybe it's pigeon poop on the detector. So they
it's like
cleaned
literally
off the detector
pigeon
really
poop.
well. Yeah,
like literally, they thought it was that. They cleaned it.
Yeah. Yeah, and they cleaned it really well. They got rid of all the pigeons. This signal was still there, and they couldn't figure out what it was. And it was coming from every direction, which, seemed like, well, that can't be something on the ground because it's in every direction we look. But it also seemed weird, like it couldn't be something in the sky either because it was the same everywhere they looked. And obviously there are things in the universe. So there's this picture of Penzias and Wilson standing in front of their crazy horn detector.
Right. The thing is epic.
Yeah. So they they had this weird thing, and so they like talked to their colleagues. They talked to some theoreticians at Princeton University, and they talked to someone called Robert Dicke. Who had figured out that if the universe, so there's a little bit of background. We know the universe is expanding. We know the universe has been expanding for a long time. If you kind of trace that expansion back, and then it back in time, then the universe must have been in one spot, or really small in the early universe. And when things are small and dense like that, they're hotter, and so these theorists at Princeton had this idea that, well, if the universe was smaller in the past and hotter and denser, then it should have been like glowing with heat, right? It should have been like sort of emitting heat in all directions, and then as it expanded, it would cool down, but that heat would still be, that glowing heat from that primordial state would still be kind of traveling through the universe as light. And so as the universe is expanding, that light from this primordial fireball is the whole universe was basically like this glowing plasma like ball of fire. I mean, not ball literally, but like the whole universe was just sort of this plasma glowing thing. Anyway, so as that radiation is expanding away, as the universe cools down, it gets kind of stretched out by the expansion of the universe. So it started out as this really hot radiation, but then it got stretched out a bit and got to longer and longer wavelengths. And so these theorists worked out that if it were really hot in the early universe and if it cooled down, then we would see the leftover radiation, basically the afterglow of the Big Bang, as microwaves, because that's a much longer wavelength. And they predicted exactly how hot it should be, what the temperature of this this background radiation should be, and they got an answer really similar to what Penzias and Wilson were seeing, which is kind of amazing. So
we're looking at here, right here.
Yeah. So if you measure the spectrum of this radiation that's coming from all directions, because every part of the universe was really hot in early times. If you look at the spectrum of that radiation, if you look at how the intensity varies with the wavelength or the frequency, you see this curve, and this is the curve that's it's called the blackbody curve. And this plot is really exciting because apparently when this plot was first shown, this was the first measurement of the spectrum of the radiation from the cosmic microwave background. Mm-hmm. When this plot was first shown, apparently people stood up and cheered. Actually, this plot got a standing ovation.
Wow.
Because
and there's not even Comic Sans on it, which
I know. So the data points on here are the little boxes, right? And those lines sticking out of them, those are the error bars. Except that's the error bars, like the uncertainty in that measurement. That's been those error bars have been magnified 400 times because the error bars are so small and you cannot see them.
That's
which means
amazing.
that the measurement is so precise and it so perfectly followed this blackbody curve. Now, a blackbody curve, it's called that for historical reasons, but what it is it's the curve, it's the radiation spectrum of something that's just glowing because it's hot. Now, anything
Right.
that's just glowing because it's hot, like if you stick a poker in a fire and it glows red, that glow is a blackbody spectrum. Now, Scott, do you have those other blackbody spectra?
Of course I do.
Okay, good.
Right here.
Um, so anything that's just glowing because it's hot follows the same sort of curve, and the where that peak lies tells you the temperature of whatever the thing is, and so the fact that the CMB so perfectly matched exactly to a blackbody spectrum,
Hmm.
that really showed you that that radiation was not, wasn't like a burst from a star or something like that. It was that the universe at early times was glowing because it was hot. Like the
Right.
universe was the whole thing was just really, really hot, really in this sort of primordial plasma state.
So I
Um,
want to go into this real quick because I
yeah.
really love blackbody radiation,
Okay.
and I love being able, I remember the first time I looked at this and really understood what it was talking about.
Yeah.
And so what we're talking, the way that it was presented to me is we're talking about the surface temperature of our star, the sun, and why, which is going to be, around in this area right
Mm,
here, and like,
yeah.
well, why does it look a certain way? Why are really hot stars blue? You think that they're only emitting blue, but they're actually no, they're getting a huge swath because there's this
Mm,
bell curve going through.
right.
And so what I really love about this, looking at these blackbody radiation diagrams right here, is that we're seeing you're having your peak emission, but you're having emission throughout a big band
Yeah.
of the spectra there.
Yeah, yeah. I mean, if you have, an incandescent light bulb, one of the non sort of futuristic fluorescent light bulbs,
Right.
um, if you have an incandescent light bulb, that's emitting light because it's got a little filament of tungsten in there, and that tungsten has been heated up so it's glowing, and that thing is just glowing because it's hot, and you see it as maybe yellowish or white, but a lot of that radiation is actually coming out in the infrared
Right.
because it is this sort of spectrum. And so one of the advantages of fluorescent light, compact fluorescent bulbs, is that they're not emitting as black bodies. They're only emitting at certain wavelengths,
Right.
mostly in the visible spectrum, so they don't sort of emit as much heat, and so they're much more efficient because they're not losing so much energy by being on that big curve like that.
Right.
So anyway, that's a bit of a digression, but yeah, blackbody radiation is really important in astronomy. When we see something that has a blackbody radiation spectrum, we call it a thermal spectrum, and that just means that it's glowing because it's hot. And tons of things do that in astronomy. But the fact that the whole universe was doing that is kind of amazing to me. It really is just the afterglow of the Big Bang, the afterglow of this primordial state when everything was dense and hot and sort of extremely energetic. So
So
anyway,
yeah, it's like
so
the snapshot.
yeah,
They're taking a picture of
yeah,
the visible beginning of our universe
yeah,
that we're actually able
yeah.
to see with light. Because even before
Right.
that, light wasn't able to escape, right?
Yeah, yeah,
So
and I think we might talk about that next time a little bit. This
right,
whole, um, like what made the difference between when it was just a fireball and when that light was sort of able to propagate, and because that's a lot of really cool stuff. But as we found, we always run out of time, and I want to show you
us.
some pictures.
Yeah,
Yeah,
we never just ramble on about things we find awesome.
no,
Ever,
no.
ever.
Um, Okay, so anyway, so they sent up this satellite called Kobe, and that's the satellite that did that spectrum that we saw. But it also took pictures of just like what the CMB looked like.
Hmm.
So can you show the monopole picture?
Yeah. Let me pull it
So
up
so this
here.
is a picture of they looked at the whole sky, and this is a projection so that you can see the whole sky all at once. Um, and what you see is this is what this is what the cosmic microwave background looked like. It was really the same in all directions. So this
Wow.
is
Yeah.
2.728 Kelvin, like to pretty high precision. It's
Right.
the same. Every part of the universe was in this hot dense state, like just like they say in the Big Bang Theory theme song. Um,
Oh, my favorite show in the world.
is it?
That was dripping with sarcasm.
Okay, good.
Lots and lots of sarcasm.
I don't want to get into the
We will talk
around
about that later. We will have an after-hours show where we find some time to just to whinge about pop culture.
Yeah.
But that is a show for another day.
Before you all jump on us, I do think the show is funny, but I also think that it's got some issues around sort of the culture of science. Not a conversation we can have today.
No.
Anyway, microwave background.
Yes.
The universe was in a hot, dense state nearly 14 billion years ago. Okay, this is what it looked like. Every direction it was just glowing with heat. So they did that. So they did that measurement, but they had really sensitive instruments on board the spacecraft CMB. Mm-hmm. And so they were able to look at sort of smaller fluctuations, and then so the next thing they looked at. Can you put up the dipole picture? Oh, just yeah, okay. So then they saw this when they looked at this is fluctuations about 3 millikelvin from the sort of average temperature. Right. So a Kelvin.
So we're
Kelvin
delta T.
Like,
so
yeah. Yeah. So the original was like 2.7 something Kelvin, which is negative 271-ish Celsius.
Super
Very
super
cold.
cold.
Yeah. So this is it's microwaves. So something that's got its blackbody peak in the microwave part of the spectrum is not very warm, but it was hot. It's just that the radiation got stretched out by expansion of the universe. Anyway, so they see this pattern, and this pattern is actually this is showing the Doppler shift from the Earth moving around the sun and the sun going around the galaxy. So what this is showing is that when in the direction of the sky where we're moving toward the sort of, I don't know, we're moving in one direction, like mm-hmm. whichever direction the Earth is moving, we see it a little bit hotter, and in the direction away from where the Earth is moving, we see it a little bit colder, and that's called the Doppler shift.
Right.
And it's just this. It's the same effect as if a siren goes by you and the pitch suddenly drops when it's going away from you. It gets higher when it's going toward you, or a race car goes like phew, like that. Like
wait, how does that go?
I'm not.
No, your audio cut out, Katie. Please.
Yeah. It goes. Yeah. It goes.
There you go. You got it that time.
Anyway, so light does the same thing, and if we're moving towards something, we see it bluer. We see it at a higher frequency. And if we're moving away from it, we see a redder, a lower frequency. So that was the dipole. But then, so they subtract that out, and then they see the next picture was the one I had with the galaxy in it. Let's see if this is right. Yeah. So then they see this, and so this is the tiny fluctuation. So this is a microkelvin, to 18 microkelvins difference between the hottest part of this picture and the coldest part of this picture. So that's still all at 2.73 Kelvin, but like tiny fluctuations around that. Right. And that stripe you see in the center, that's the galaxy. So the galaxy is also glowing, and there's also radiation coming from the galaxy. And so if you want to know what that primordial radiation looked like, you have to kind of subtract that out too. And so we have, actually, can you show that picture of the galaxy in this projection? Because I think that's a really cool picture.
Yeah, let me pull it up here.
Okay. Because we live in a galaxy, and it's really inconvenient, and I'll talk more about that.
But it's also nice that we live in a galaxy.
Yeah, but like, for cosmology...
If we were just a star roaming around in intergalactic space, I don't think that would be a good time for us. Pretty sure.
But it would be so much easier to do cosmology.
Yeah.
Because the galaxy is such a pain for trying to see things that are really distant.
Right.
It just really gets in the way. It blocks out huge portions of the sky. It's got its own radiation going on.
Is this the image you're looking for?
Yeah. So this is a great picture. This is a survey called 2MASS, where it's an all-sky survey. So it's again this projection where every part of the sky is on this projection, and it's centered so that the center of the galaxy is in the middle of the picture. You can see the galactic bulge, and you can see like the disk of the galaxy, those dust lanes in the plane of the galaxy, and you can see the large and small Magellanic Clouds, these satellite galaxies in the south there. And so anyway, so it's a really neat thing, but that galaxy is emitting some radiation at microwave frequencies, and so when you try and see the CMB, you get this swath of galaxy in the middle.
Right.
So you can try and correct for that, and if you correct for that, you can see the fluctuations in the actual cosmic microwave background. So do you have that Kobe picture?
I believe I do. Let me see.
Okay. All right.
So this one, I have so many pictures. Yeah, I believe this is it.
Yeah. So this is beautiful. This is the first picture we ever had of the actual fluctuations in the cosmic microwave fireball, like the primordial fireball, and these are tiny fluctuations. These are like 1 part in 100,000 or something from this sort of average temperature of 2.73 something Kelvin. So these are places where it's a little tiny bit hotter and a little tiny bit colder. And these fluctuations, these sort of trace out where, like, how matter was distributed at the very earliest moment of the universe. This is sort of like the first baby picture of our whole universe.
It's so cute, though.
Yeah. And those tiny fluctuations, like there's a little bit more matter over here and a little bit less matter over here, and to tiny levels, like 100 part in 100,000. Those little fluctuations turn into galaxies. Gravitational collapse happens. You have a little tiny bit more mass here, a little tiny bit less mass here, and you get mass coming over and collecting in where there's already mass by gravitational collapse, and then that kind of comes together and it gets more compressed, and then stars form, and then galaxies form.
So I'm sure this question was raised then, which what I guess would make sense. Why isn't it smooth? Why? When that happened, why is it lumpy? Because
so I think we're gonna have to talk about that next time, because
I think so.
That gets into inflation theory, and that gets into quantum fluctuations, and it's a long story.
And is it that we're still trying to figure that out?
And we're still. I mean, we still don't know for sure. There's some theories that can explain these fluctuations in the cosmic microwave background. Basically the primordial fluctuations, the initial state of the universe that led to all the structure we see today. And we're still kind of weighing up different theories and trying to really understand how that all came about. And the best idea we have so far is called inflation theory. And there are some problems with inflation theory, and it's not a sort of complete, theory with fundamental physics basis yet. We're still kind of trying to figure out how it works together with everything else.
And we're still getting science in on that right now.
Sorry?
We're still getting new research in on that. That's being hotly debated. If you guys have been following the big science news this year, we've had some really awesome stuff coming out of Antarctica, and it's going back and forth. Like, okay, and I think it brings up a good question here that Tom asked, Nathy, pull up here, says, how do the researchers get the probes to calibrate that so accurately?
It's a big challenge, and that's one of the things that makes these measurements so difficult. I mean, you have to make sure that your own your spacecraft is cold. If you're doing it in space, which most of these things are done in space because microwaves don't come through the atmosphere very well.
Right.
If you're doing it in space, you have to make sure that your spacecraft is really, really cold and doesn't, heat up with the sunlight, and when it's in the shade or not, based on where it's going around the Earth, or if you put it somewhere else, you have to keep it in a really like stable temperature state so that it can measure the temperature of the radiation coming in, and that's really difficult. And so there's just a huge amount of work that goes into testing these different kinds of detectors and calibrating them in various ways and doing all these cross checks. And some of the recent some of the sort of biggest arguments, what we call experimental cosmology. So looking at things like the cosmic microwave background with these detectors. Some of the biggest arguments come in trying to properly calibrate the detector and trying to figure out how to keep the temperature stable and how you make sure that you're really getting the right number. I mean, so there have been, since I've been doing cosmology, there have been two big experiments. One is called WMAP and one is called Planck.
Right.
WMAP was the earlier one. Do you have the picture of the
Yeah, I do.
WMAP CMB?
Yeah, right now.
Okay.
So here is WMAP, which is actually has been one of the backgrounds on it's on my laptop actually, because I just love it. It's amazing. It's so pretty and
Yeah.
it's
Yeah. So it's a lot more detail than
right.
the Kobe image, and you can see even smaller fluctuations in that kind of microwave background. Now that experiment I believe it was like a differential measurement, so it was looking at one part of the sky and subtracting the temperature from the other part of the sky, and that was how it calibrated itself and
Okay.
made sure that it was getting the right temperature. The next iteration, and also WMAP was passively cooled, so it had some kind of radiation thing, so that it didn't have to have like a coolant on board. It had a way to radiate out heat.
Right.
The new one, Planck, which is up there right now, has been doing a lot of data taking and putting out some results recently. It's given us this even more detailed picture
Right.
of the cosmic microwave background. It actually has a coolant on board, and it kind of has this temperature, this sort of temperature curve that goes up and down based on when it's got the coolant active, or how it sort of cools itself, and then it turns, and then it radiates, and it's that's a lot more complicated, a coolant system, but it's also a much more detailed instrument, as you can see by the improved resolution here. So it's a challenge. I mean, this is one of the hard things, and also trying to deal with the galaxy. In these pictures, you can see the galaxy has been subtracted out in the center, and that's a hard thing to do, and there's a lot of work that goes into that. So yeah, it's a very complicated measurement.
Right. And I mean, it's gorgeous. I mean, we're literally looking at the it just blows my mind thinking that what is going on with cosmology, or modern cosmology, is that we are trying to find ways to experimentally observe the very beginning of the universe, 14 billion years ago, and we're trying to directly detect it, not just like infer different things, we're trying to directly detect what was going on as early as we can after the Big Bang.
Yeah,
and
so this
it
is, yeah. So the cosmic microwave background, that's the state of the universe at, I believe it was about 380,000 years after the Big Bang. Now the universe is about 13.8 billion years old.
Right.
So 380,000 years, it's not even halfway through its first billion years. So really early on. And it's funny to think about that, because these fluctuations, these 1 part in 100,000 fluctations at the cosmic microwave background state, those have been growing for 380,000 years.
Right.
Or I mean, the thing is, they weren't growing at first because the universe was full of radiation, and it kept these fluctuations from really growing. But after 380,000 years, there were still only these tiniest fluctuations in the density of different parts of the universe. And once the cosmic microwave background was released, I mean, once you got to the state where the radiation could pass away freely, and you didn't have this, we'll talk about this later, but this sort of mixing of the radiation and the matter, then you were really able to have fluctuations grow, and the galaxies form, and clusters and everything like that. So this is really like the start of the growth of structure of the universe. Before that, it was all this sort of plasma, and they had these tiny fluctuations, but they weren't really doing anything. And then at this point, that's when everything really got started, which is pretty exciting.
Yeah.
And we can see that. You can see it directly in radiation, in electromagnetic radiation, in light.
Right. I mean, like it comes with everything that we're looking at every single day. We're looking into the past, just because light has a speed limit. It goes through a medium. We're always seeing things as they were. But the fact that we can look that far back and be able to understand why things are working the way they are now, and through different epochs, I mean, it's amazing. It excites me so much about the fact that we're still looking at, it took something that, like, why are we getting this, it must be pigeons, let's go scrape off the pigeon poop. Or, another thing I heard too, which I haven't actually seen any research on. It's something that's like, it sounds good, but I haven't, but it's, depending on the frequency there, that like back when, so I know some of you are a bit younger than us watching this. So back in the day, we used to have televisions that you could turn knobs, and you would have snow on the screen. And so you have the static, and I believe like what 1% of the static showing up there was actually that microwaves coming in and being picked up by the antenna because it was at the right frequency to be able to be picked up by the antenna, and it displayed on your cathode ray tube television.
Yeah, I don't remember exactly what percentage it was, but yeah, like some order 1% amount of the static on your TV was the cosmic microwave background, was the afterglow of the Big Bang coming to your television.
Right, you're watching the beginning of the universe all the time. You know, it's every channel. Oh, this show again, all the time. What's going on? But it's so cool that we're just by understanding how the way that light interacts with matter. And how now we know with Doppler shifting and that the blackbody radiation, everything like we were watching the Big Bang for so long without a crappy jingle and bad stereotypes about people in Caltech, but we've been able to see it, and we will not get on this soapbox, I swear. But it's something that we've been seeing for so long, and now we're able to understand why it's there, and look at that, and go from this noise to getting these extremely, extremely detailed maps of 380. It was 380,000 years after the Big Bang. That's such a small amount of time. Such a small amount of time.
Yeah. And the other thing that, I mean, I don't have time to go into this, and I should check some of the math, but in some number of billions of years from now, it will not be possible to see the CMB. We're actually really lucky because as the universe is expanding, the cosmic microwave background is being stretched out to lower and lower frequencies. It's getting to lower and lower temperatures in terms of the cosmic microwave background, getting less intense. And we're not going to be able to see it, not only because it's being stretched out and going to lower frequencies, but also because of the way the universe is expanding. The acceleration is taking things sort of out of our horizon in a sense, and it's going to make it harder and harder to see things that are really distant. And if we were existing several billion years into the future, we might not have been able to see the CMB, and we might not have been able to learn about that earliest time in the universe. And we've learned so much from the CMB. About how the early universe worked and where it all came from, and we're still learning new things all the time by examining that light more and more carefully. And so we should feel very lucky, I think, that we can know about this and learn something from it.
Absolutely. So because about time for us to go here. So if I'm seeing still a bunch of actually comments on, but some really good ones. So this is more of a primer. We're going to be digging a little bit deeper into CMB for the next at least 2 episodes. But knowing us, you never know. We just might go for like 10 because we can. So if you guys have any questions regarding CMB, what we're learning about it, or anything like that, let us know in the comments below over here on YouTube. Also, I will try and check in with the Q&A app as well. And we're at Twitter, so Katie, where can, because I know people ask you science questions all the time on the Twitters. So
I do my best.
Where can people find you?
Well, people can find me at AstroKatie on Twitter. And I'm also I have a Facebook page, facebook.com/AstroKatie. I don't update it as frequently, but you can get into conversations there in a sort of different way than on Twitter. And I'm on Google Plus at +Katie_Mack. And you can find more about my writings and what I've done in various other places at my website, astrokatie.com.
Nice. But I wasn't joking. She has 14,689 followers on Twitter. And I also found out that you were the most followed astronomer in Australia. So
yeah,
that's pretty awesome. And
Yeah,
and
it's
for the
cool.
future, this little teaser, because of that super secret thing we're talking about, you will find out a little bit more about that, including a really awesome gift that I did not know about until I was editing that footage. So,
A really awesome
um,
what? Oh yeah, yeah, yeah,
gift,
yeah,
gift, yeah.
yeah. Yeah.
So, I am Scott Lewis. You can follow me on Twitter at Scientific Scott. This has been our first hangout on Know the Cosmos. You can follow us on Twitter at Know the Cosmos. Also, I'll be doing a write-up tomorrow about the show with all the images in one place. So if you want to bookmark the website knowthecosmos.com, and we're all over on Twitter, Facebook, Google+. And I think I have a Tumblr somewhere, maybe, that I might use if I have time.
And if you do have more questions about CMB, come back next time because we'll talk about it some more, probably in 2 weeks.
2 weeks. 2 weeks,
same
for
time.
sure.
Yeah.
Same, yeah, because I don't need to sleep. Come on. It's Friday night. I'm in LA. Let's do this.
Oh, and one more thing. If you're in California or like the west coast of the U.S. or the east coast of Australia or somewhere in the middle, you'll be able to see a lunar eclipse on Tuesday night.
Tuesday night.
Or maybe it's I'm not sure. It might be Monday night for you. But check it out. Look up lunar eclipses coming up. There's one really soon, and you should watch it because lunar eclipses are awesome.
Lunar eclipses are awesome. Is it going to be total? Or
yeah.
Nice.
It'll be. I think for both you and me, it'll be visible as a total eclipse, total lunar eclipse, which is where the sun. Let's see, there's the sun here and the Earth here, and then the moon goes behind into the shadow of the Earth.
Right.
So it's in red, which is
we just had one here a few months ago. We did a broadcast over at Spaceman News on it. So
yeah, there's
might have to do that again.
Yeah, there's like a series. Sometimes you get like a tetrad. It's called a tetrad, where you get several in a row, spaced out by several months. But anyway, so there's going to be one of those. You'll have to stay up really late to watch it. I will not. I think it'll be over by like midnight for me. But anyway, it'll be fine.
I stay up till midnight for you. Why don't you stay up till midnight for me? I know. I'm not feeling.
I'll stay up till midnight for the eclipse.
Well, you watched it rise with me. You were in that show with me, so you were actually watching the moon rise, completely eclipsed at the time. It was so awesome. So
cool.
That is over on the other channel at Spaceman News. So you want to check that out on YouTube. We have that up. We were broadcasting for a while, but it's awesome. So we love doing stuff like that. And I know that planetary science is not your typical wheelhouse, but I'm sure I can convince you to talk about some planetary science. And I've taught some planetary astronomy as well, so maybe we can dig into some other things. So if you guys have any other topics you want us to cover in the future, you can have a conversation with an astrophysicist like we are now. So thank you all for watching, and we will see you all next time.
Bye.